At that moment when we first learned to measure seconds and hours, humanity had already peered into the very fabric of the world, into what we habitually call time. But what kind of phenomenon is this? Something objective in the universe, or a subtle construct born of our perception? This question has haunted scientists and philosophers ever since Albert Einstein rewrote the structure of the physical world. He discovered, time is not timeless and not the same for everyone. If you sit in a rocket, accelerate to a significant fraction of the speed of light, and return to Earth, then your clocks will show less elapsed time than those of the people who stayed on the surface. This is how time dilation predicted by the special theory of relativity works. Moreover, near massive bodies, such as black holes, the flow of time slows down relative to a distant observer, a direct consequence of Einstein's general theory of relativity. You and I live in a world where time seems linear. It flows from the past to the future. But modern experiments show that our familiar sense of time is merely the tip of the iceberg. In the quantum world, the world of atoms and photons, the concept of time turns out to be even stranger and more elusive. For example, in classical quantum mechanics, time is traditionally considered an independent variable. But when trying to unite quantum physics with gravity, deep problems arise. This is known as the problem of time. Quantum mechanics and general relativity understand time differently and how it is incorporated into the fundamental laws of nature. To make it clearer, imagine two different instruments for measuring the world. One is quantum mechanics. In it, time is like a straight ruler on a table. It simply exists. It is the same for all processes, and we just watch how particles change over time. Time itself in quantum physics does not participate in events. It is like a background, like a clock on the wall. The other instrument is general relativity. Here, time is no longer a ruler, but an elastic fabric. Mass and gravity can stretch it, compress it, slow it down. Near a black hole, time flows differently than far from it. It becomes part of what is happening rather than just an observer. The problem arises when we try to combine these two instruments into one. It is as if some clocks always run the same way, while others start changing their pace depending on where you stand and how you move. They cannot agree on what 1 second is. And it is precisely this mismatch in understanding time that is called the problem of time in modern physics. Some modern physicists go so far as to question the very existence of time as a fundamental entity. In a theory published in the journal Physical Review, it is suggested that time is an illusion arising from quantum entanglement. That is, what we perceive as a flow of events may be the result of a complex network of interconnected quantum states rather than an absolute physical variable existing on its own. To understand how deep this riddle is, imagine a photon, a particle of light. For it, when it moves at the speed of light, classical physics asserts, time effectively stops. Not a single tick of the clock will pass for this photon between departure and arrival, no matter how far it flies. This is an amazing consequence of relativistic transformations, where the speed of light in vacuum is the universal limit. But what if instead of one truth about time, there are countless multitudes of them? Imagine a train that accelerates faster and faster. The closer it gets to the limiting speed, the slower the clocks inside the carriage start to run, compared to the clocks at the station. Now imagine the extreme case, a train traveling at the speed of light. For the passenger inside such a train, time seems to stop ticking altogether. The path from departure to arrival collapses into one moment, as if you blinked and immediately found yourself at the end of the path. We cannot become a photon, but the mathematics of physics says, for light, there is no road in time, only distance in space. This is like a movie frame that never changes to the next one. And this is precisely why a strange thought arises. If for light time does not flow, but for us it does, then time is not one for everyone, but depends on who and how they move. Perhaps the universe has no single time. There are many times, as many as there are ways to look at the world. The great physicist John Wheeler, one of the pioneers of quantum gravity, repeatedly emphasized that the concept of simultaneity breaks down into the atoms of physics, and that space-time itself may be the result of more fundamental structures. He posed a provocative question: is not space-time itself, including time, a product of acts of observation? In quantum mechanics, the act of measurement not only reveals the state of the system, but also determines it. This idea leads us to the thin boundary between the observer and the world, between the time that we fix and the time that exists beyond our perception. But physics is only one side of the coin. In philosophy, from ancient times, the question of the nature of time has troubled thinkers. Aurelius Augustine, in the 5th century, admitted his powerlessness in explaining time. How can one understand that which is not in the present, which no longer exists or has not yet come into being? Einstein, in turn, defined time as that which clocks measure, emphasizing its connection with physical processes rather than some abstract entity. Imagine yourself on a spaceship gliding near the event horizon of a black hole. You feel every moment, but external observers see your clock slowed down. Outside this gravitational well, the flow of time is different. Such a reality makes the concept of common time meaningless. Each observer has their own temporal flow, and this is not a philosophical metaphor. It is what Einstein's equations predict and confirm. When we look at the world from the perspective of quantum physics and cosmology, it seems that our familiar linear arrow of time is no more than an illusion, a convenient way to order events. But perhaps behind this illusion lies something much more mysterious and fundamental. Not a flow, but a network of interconnected states in which the past, present, and future are interwoven much more deeply than we could have imagined. When humanity first tried to measure time, it did not know that with this gesture it was changing its place in the universe. The first clocks were not mechanisms, but shadows. A stone stuck into the ground cast a line, and by its movement, ancient peoples understood. The world lives by rhythms greater than man. The sun rose and set. Stars returned to their places. Seasons replaced one another. Time then did not flow. It returned. In ancient civilizations, time was a cycle. In Mesopotamia, Egypt, among the Maya, and in China, the past did not disappear forever, but re-entered the present. Man felt himself part of a vast cosmic breath. His life was a short wave on the surface of an infinite ocean, and measuring time meant not controlling it, but adapting to it. But gradually, the view changed. With the advent of water clocks, hourglasses, and the first astronomical tables, man began to fix not just rhythm, but duration. Time became a segment. It could be divided, compared, counted. And at that moment, the universe seemed to step back, yielding place to man as the measurer. The real revolution happened in the era of mechanical clocks. Medieval tower mechanisms did not just count minutes. They disciplined society. Prayers, markets, labor, sleep, everything came under the sway of the hands movement. Historians of science say it was clocks, not telescopes, that became the main tool of modernity. The world began to be perceived as a mechanism and time as an evenly ticking machine. Isaac Newton cemented this sensation in physics. For him, time was absolute, flowing equally everywhere, independent of the observer and events. It existed on its own, like a stage on which the cosmic spectacle is played out. This idea gave man a sense of stability. The universe obeys laws, and time is a reliable background that will not deceive. But it was precisely this confidence that prepared the ground for its destruction. When at the beginning of the 20th century, Einstein proposed the relativity of time, he did not just change formulas. He knocked the ground out from under human consciousness. It turned out that clocks run differently depending on speed and gravity. That there is no universal now. That two events simultaneous for one observer can be separated in time for another. Humanity suddenly lost its privileged reference point. We were no longer at the center of the temporal axis. Our clocks ceased to be the standard of the universe. Curiously, this discovery coincided with the era when cinema learned to edit time. Films first showed the past can be glued to the present, the future intruded into the frame, and linearity violated. Art intuitively sensed what physics was only beginning to realize. Time is not a straight line, but a structure. Later, atomic clocks made time even more precise, and even stranger. They measure atomic vibrations, not the movement of hands. Today, thanks to them, we know. Time flows slightly faster at the top of a mountain than at its base. This effect is so real that it has to be taken into account in the operation of navigation satellites. Otherwise, GPS would simply be wrong. It turns out that every step toward precision distanced us from the illusion of a single time. The more accurately we measured time, the less it resembled something simple and understandable. It ceased to be a background and became a participant in events. And man, not a master, but a local observer, squeezed between the speed of light and the curvature of space. We no longer stand at the center of the universe and do not live in its single now. We move within a multitude of temporal flows, each of which depends on where we are and how we move. And perhaps this very understanding became the first step toward the next riddle, the question of why time has a direction at all. If time is not absolute, if it depends on motion and gravity, a more troubling question arises. Why do we feel it as directed? Why does the past seem fixed and the future open and uncertain? Why do we remember one and never the other? In physics, this is called the arrow of time. Newton's equations, Maxwell's, and even the equations of quantum mechanics are almost always symmetric in time. They work equally well forward and backward. From the point of view of fundamental laws, nothing prohibits a cup from reassembling from shards and flying onto the table. But we know this does not happen. The reason is hidden in the concept of entropy, a measure of disorder. The second law of thermodynamics states in a closed system, entropy does not decrease over time. Order tends to chaos. Ice melts, gas dissipates, structures decay. This is the physical basis of the arrow of time. Any ordered structures over time tend toward disorder. This growth of disorder, entropy, shows us that time goes forward. We sense time precisely through such changes. Order turns into chaos, and by this process, our brain understands that some event has passed, and the future has not yet arrived. It is important to understand entropy does not speak of destruction in the everyday sense. It speaks of probability. Disordered states are simply much more probable than ordered ones. The universe chooses not a direction, but statistics. Physicist Ludwig Boltzmann understood as early as the 19th century. The sensation of time is connected not with time itself, but with the growth of entropy. His ideas were so unusual that he became the object of ridicule from contemporaries. But today, it is precisely they that form the basis of our understanding of irreversibility. However, a new riddle appears here. If the arrow of time is set by entropy, why does it coincide with psychological time? Why do we remember the past and not the future? Why does memory work in one direction? Modern neuroscience shows memory is a physical process. Remembering requires energy and is accompanied by an increase in entropy in the brain. When a memory is formed, neural connections are restructured, heat is released, disorder grows at the microscopic level. Memory is possible only because entropy increases. The future is not remembered because it has not yet existed in a physical sense. Energy dissipation has not occurred, traces have not arisen. The past is not just what happened, but what left imprints in the brain, in the environment, and in the structure of the world. Philosopher Jorge Luis Borges wrote that memory is a form of time, but physics clarifies memory is a trace of entropy. We move to where traces have not yet appeared. Interestingly, at the fundamental level, quantum mechanics does not require an arrow of time. Some interpretations allow processes where cause and effect switch places. Experiments with quantum entanglement show correlations that do not fit into the usual temporal sequence. And yet, in our macroscopic world, the arrow of time is stable. It is built into every cell, every memory, into the biography of the personality itself. We age because entropy grows. We remember childhood because the traces of the past are deeper and denser than the fog of the future. There is also a cosmological aspect. The arrow of time is linked to the initial state of the universe. After the Big Bang, it was remarkably ordered. This low entropy beginning set the direction along which everything unfolds. Why the universe started exactly that way is one of the deepest questions in modern physics. Cosmologist Sean Carroll compares time to a river flowing from an unusually smooth source. We float along it not because time pushes us, but because the structure of the universe makes movement in the opposite direction almost impossible. And then a nearly philosophical thought arises. Perhaps time is not that in which events occur, but that which happens when the universe forgets its past. But if so, what will happen when entropy reaches its maximum? Will time disappear along with memory, or will it take a form inaccessible to our experience? Answers to these questions lead us even further, to where the cosmos approaches its limits, and time begins to behave as if ready to dissolve. If the arrow of time is born from the structure of the universe, it is logical to ask, what happens to time where the structure of space itself breaks down? Cosmology, the science of the entire universe, shows time does not behave the same everywhere. There are regions where it stretches, and places where it possibly ceases to exist altogether. Black holes are the most radical example. They arise when a massive star collapses under its own gravity. At the center, a region forms where density becomes extreme, and the curvature of space-time infinite. The boundary of this region is called the event horizon. For an external observer, everything approaching the event horizon seems to freeze in time. The clocks of the falling object slow down, its light reddens and disappears. In the limit, it seems it never crosses the boundary. But for the falling observer themselves, everything is different. Their own time flows normally, and crossing the horizon happens in a finite interval. That is, the object fell into the black hole long ago, but for the external observer, it appears frozen at its edge. This means a strange thing. Time depends on the point of view so radically that two descriptions of one reality become incompatible. There is no single history of events. There are different temporal narratives existing simultaneously. What happens inside a black hole is one of the main riddles of physics. The equations of general relativity point to a singularity, a point where familiar concepts of time and space lose meaning. There, one cannot say what will be later, because later itself ceases to be defined. Some physicists suggest that inside a black hole, time and space switch roles. The direction toward the center becomes as inevitable as movement into the future. In this sense, falling to the singularity is not a choice, but a temporal necessity. But black holes are merely local laboratories of time. Cosmology looks further, to the fate of the entire universe. According to modern observations, the universe is expanding with acceleration. This discovery is linked to the work of astrophysicists studying distant supernovae and led to the idea of dark energy. If the acceleration continues, space will stretch faster and faster, galaxies will disappear beyond the observable horizon, and physical processes will become rare and cold. In such a scenario, the hypothesis of the heat death of the universe arises. Entropy reaches a maximum, differences smooth out, energy is distributed evenly. Without gradients, there are no processes. Without processes, there are no changes. And without changes, is there time? Some cosmologists say cautiously, in a state of maximum entropy, time loses meaning. It does not disappear, but becomes indistinguishable from immobility. The universe continues to exist, but nothing happens in it anymore. There are more radical ideas as well. In quantum cosmology, the hypothesis is put forward that time is an emergent phenomenon arising only under certain conditions. When these conditions disappear, time disappears too. Not stops, but simply ceases to be a defined concept. Physicist Carlo Rovelli writes that in the fundamental equations of quantum gravity, there may be no time at all. It appears only at the macroscopic level, just as temperature arises from the motion of molecules but does not belong to a single particle. If this is so, then the end of time is not a catastrophe, but a return to a deeper reality where there is no before and after. There is only a structure of interconnections. Curiously, similar ideas are found in philosophy as well. Some schools considered time a property of consciousness, not of the world. Cosmology, unwillingly, brings us back to this boundary once more, where physics ends and the question of the observer begins. When we look at the night sky, we see the past. Light from distant galaxies has been traveling to us for billions of years. But if the universe is moving toward a state without changes, perhaps one day there will be no one to look and no one to count. And then the last, strangest question remains. If time is not fundamental, if it arises and disappears, then what lies beyond its limits? Answers to this lead us not only into space but also into human experience, to where the very sensation of now is born. If time can disappear in equations, dissolve in black holes, and lose meaning at the edge of the universe, the last bastion remains: human experience. We live in time not because we know formulas, but because we feel now. This feeling seems the most reliable and the most mysterious. Consciousness does not perceive time directly. We do not feel seconds or minutes. We feel changes, movement, expectation, memory. When there are no changes, time seems to disappear. In deep meditation, in the flow of creativity, in moments of danger or love, clocks lose power. Physical time goes on, but psychological time stops coinciding with it. Neurobiologists show the brain has no single time center. The sensation of the present is assembled from many processes: memory, attention, prediction. We constantly model the future and compare it with what has just become the past. The present is not a point, but a thin interval of assembling experience. And here, physics approaches philosophy again. In quantum mechanics, the observer plays a strange role. The result of measurement does not exist until the act of observation in the usual sense. The state of the system is described by probabilities, and only interaction with the measuring device, and ultimately with the observer, makes the outcome definite. Some interpretations of quantum mechanics go further and suggest time may be linked to the process of observation. As long as there is no observation, there is no definite sequence of events. Reality exists as a set of possibilities, and time arises as a trace of fixation. Physicist John Wheeler formulated this radically. The universe is not a machine, but a process of participation. Observers do not just look at the world, they participate in its becoming. The past, in a certain sense, is formed retrospectively, through the traces we discover now. This idea frightens and inspires at the same time. It does not mean that consciousness creates the universe, but it hints, without observation, there is no history. Without history, there is no time. Philosopher Henri Bergson distinguished measurable time and duration, the inner flow of experiences. Physics long ignored this difference. But today, when time disappears from fundamental equations, we have to return to this distinction. To live in a universe where time may be an illusion means to live without guarantees. There is no absolute future toward which everything goes. There is no universal now shared by all beings. There are only local perspectives, temporal islands of experience connected by a network of causes and probabilities. And yet, it is precisely in this world that meaning becomes possible. If time is not given from outside, it becomes valuable from within. Every moment is not just a point on a line, but a unique intersection of memory and expectation. We do not move through time, we live it. The cosmos may be cold, infinite, and indifferent, but within it arises consciousness capable of remembering, hoping, and asking questions about its place. And perhaps it is precisely this that makes time real, not as a physical entity, but as a form of meaning. When we look at the starry sky, we see the past. When we close our eyes, we experience the present. When we ask questions, we reach into the future. In this simple threefold gesture lies human time. Beyond formulas and event horizons, beyond beginning and end, one thing remains: the experience of being. And as long as it exists, time, no matter how illusory, continues.